Great. All right, guys. So welcome back. This is the second lecture. So it's application. So that means we've already covered the fundamentals yesterday, but I'll still go through some of the things that we've discussed earlier on yesterday. All right. So just to recap, we know that I is root minus 1, aka the imaginary number, because there's no number. I mean, it's not legit, supposedly, but then mathematicians try to be smart, make a whole new branch of mathematics because they just want to. That's actually a true story. All right. Now, then we also learned that there are three ways to represent complex numbers: x plus iy, your Cartesian; r cosine theta plus r sine theta, your trigonometry; and then the best form, REI theta, the exponential form. The modulus of Z we talk about is the magnitude of Z. So it's very much the same as the distance between 2 points in your Cartesian plane. But of course, in complex numbers, the 2 points will be, one of them will be the origin, and then the other will be the complex number. That's why it is simply the square root sum of squares, x squared plus y squared, which is also your kind of your Z conjugate, but it's actually the square root of your Z conjugate. All right. So argument of Z equals to argument of Z. So we represent arc Z equals to theta. I think someone wants to join. Can someone help me admit Zach?
Wait.
Yeah.
Coming.
Then you know that the principal range of our argument is minus pi to pi, inclusive of pi only. All right. But then again, I just want to emphasize this is a principal range. So if your argument, let's say we see a complex number with a argument that's outside this range, so let's say minus 4 pi over 3, then it is still a complex number. It's just that its argument is not in the principal range. All right. So to find the argument, we use the idea, or we use the familiar idea of the basic angle. All right. So we also introduce the Argand diagram. So of course, let's say we have a random point. Let's say we have this point here. This would be our modulus, right? This length here. The hypotenuse will be our modulus, R or mod Z. Then this will be our argument. Our argument is always measured from the positive real axis anti-clockwise, just like your Cartesian coordinates, Cartesian axis. Of course, then if you measure it in clockwise, then it will be the negative side. All right, so positive side is always anti-clockwise from the real axis. So some of you might still be confused about your basic angle. Someone wants to join, is it? Okay, hold on.
Wait. Got it.
Okay, so we want to talk about basic angles. So we got a question earlier today, and I think let's just iron this out once and for all. Although this should be kind of be covered in secondary school, but nonetheless, let's cover it now because I can't. I prefer to tackle the problem instead of just saying, oh, secondary school. All right. Basic angle, essentially, you draw a triangle and then the angle that is at the origin. All right. So this angle here, as you can see, the alpha angles for the respective quadrants 1 and 4, first and fourth quadrant. Of course, then you have to find the argument. So it will just simply be theta will be measured from here to the complex number here. So this is our complex number. And then it will just simply be your basic angle. Then our fourth quadrant, you notice our basic angle is below the real axis. So it's measured in the clockwise from the real axis. So it will be negative basic angle. All right, so this is your first and fourth quadrant. Then we talk about the basic angle from our second and third quadrant. You notice that our basic angle would still be on the left side. So again, it's the angle within the triangle that is at the origin. So our alpha will be here as marked out by the two triangles. And our argument would then simply be written out here. So the second quadrant would be our pi minus alpha, right? I think you guys can know why. Because if let's say we go from here to all the way here is pi minus away this alpha to give us pi minus alpha, the argument of the complex number. Same thing for the bottom third quadrant. We have from here to here it is minus pi, all right, because it's now clockwise from the real axis. So we then minus away the alpha. No, we plus the alpha because basic angle is always positive. All right. If you minus more angle, which means that you're going to go further further clockwise. All right. So it is plus, right? Don't forget, it's now pi is measured this way. If you add a positive angle, you'll go back down again. All right. So that is how you calculate your argument for the various quadrants. Okay. So counting by recap, again, Z conjugate equals to a squared plus b squared equals to mod r squared gives you a real number. So this is important when you talk about rationalizing the denominator or solving some of the weird questions that you see later on. And again, just to emphasize again, Z conjugate, basically your imaginary is flipped in terms of the sign. Lastly, we have the few identities for complex numbers. Mod Z mod W equals to mod Z times W. And the argument of Z W is simply like your logarithm arc Z plus arc W. These are all proven by your exponential form. All right. Same thing for our Z over W, or proven by your exponential form mod Z over mod W will be the modulus of Z over W, and then the argument again behaves like your logarithm. Again, proven by modular exponential form, mod of Z power n equals to the nth power of mod Z. And argument of Z power n is really the same logarithm. I keep saying this. You bring the power down and Z. So n times Z, argument of Z. All right. Lastly, and I know I emphasized this again yesterday. I emphasized this yesterday, and I'm going to emphasize this again. All right. So this are the relationship between the different arguments. All right, theta to minus theta because your imaginary is now flipped. So if I were to draw the Argand diagram, it is your theta, it is your complex number, your negative, your conjugate is just the opposite because your imaginary is flipped. So it just be a reflection about the real axis. Your argument is now in the clockwise direction. Then for Iz minus Z and minus Iz, you just use the idea of EI pi over 2 times Z. Then this will be EI pi, then this will be EI, well, minus pi over 2. All right. And there you go. Okay. Yeah, I think this should be plus theta minus pi over 2. But actually, they will give you the same angle if I'm not mistaken. Yeah. Actually, no, sorry. This is theta minus pi over 2. Yeah, this will be theta minus pi over 2. I will make that edit later on. And then finally, we have the half angle trick, or I like to call it the average angle trick. Again, super important. Please, please, please remember this. I'm begging you guys. All right, I don't know why I'm begging you guys, but I'm just gonna. I urge you guys to really remember this technique. All right, in case it does come out again, which I have a feeling it might. So using these identities, the RI theta minus RI minus theta or RI theta plus RI theta, and these are the things to take note of, right? Basically, look out for this particular form, or as you see in an example later, a slightly different form, but it's still usable. All right.
All right. I'll be mainly covering the algebra and polynomials part of complex numbers. So a lot of algebraic manipulation coming your way. Okay, so bear with me for a while. Okay. Next, we got this finding the square roots of the complex numbers. Okay, I think we actually did a similar question yesterday. You write out the complex number that you are trying to find in terms of A and B, alright, as you can see here. Okay. Suppose we have a square here. Sorry, I didn't write it down. So it's A plus BI square, alright? So this is A plus BI square. That is the complex number. Note that's the solution that you wanna find, okay? So what we are trying to solve here is for A and B. Those are your two unknowns. That's what you're trying to find. Okay, so now you get this. So when you square both sides, you actually remove the square root, and you get 4 plus 3i equals to a square plus 2abi minus b square. Okay, this is basically the expansion of your squared complex number. All right. So now you look at both sides and then you do your comparison. Okay, a square minus b square, as we have already stated here. This is quite important actually. A square minus b square will actually give you a real number. So a square minus b square will correspond to the real side of your complex number. Okay, so this is what we have written down over here. All right. Then next, you have to compare the imaginary side of the complex number. Okay, so I'm just going to change color here. All right, so your 3i will correspond to your 2abi. And And that's what we have done here. Okay. Now you see that you have made two equations for yourself, and this is your perfect opportunity to do a simultaneous equation to solve for A or B. Okay, depending on which one you put as the subject. By manipulating equation 1, you end up getting A or B first. Alright. So for me, I manipulated A such that A is the subject, and then next we'll sub A equals to 3 over 2B into this equation here. Alright. So now you manipulate it, manipulate. I won't go through the manipulation because I think you guys should be able to do it. Then you get this. Alright, you expand it and you simplify it or whatever. Manipulate it such that you get this. A lot of people will stop here and get stunned because they see, the index is 4. How do I solve a polynomial in terms of with the highest index as 4? Alright, but then you realize that it's 4, 2, and 0. So basically what you can do is you use your x squared minus b squared plus c as a model. You will find for b squared instead. Okay. Now, must take note that b is always real. Okay. So b squared will forever be positive. And because of that, when you factorize this, you get the answer 2b squared minus 9, which is not a possible answer, so you just reject it. Alright. And then the other solution will be 2b squared equals to 1, which will solve for b to give you plus minus 1 over root 2. So for myself, what I like to do is to rationalize the irrational number. Okay. In my workings, of course, when you give your answer, some teachers will advise you to, some teachers will say, screw it. Okay. Make sure that you got your plus minus sign, because a lot of people forget the plus minus. Okay. So because there's a plus minus, you get multiple solutions. After you solve for b, right, what you just do is you sub it back inside here, okay? Very simple. And then for the positive value of b, you get a positive value of a, which gives you this. And then when you sub in the negative value of b, it will give you the negative value of a. Okay, so the solutions are as follows over here. Okay, very simple. All right, move on to the next question. So 7 squared equals to 9 minus 8i. What you do is, honestly, is the same as the previous question, except now you got all these really nasty as square root within a square root. Okay, that's the only hard part lah, honestly. Okay, so similarly, they've already given it to you lah, honestly. So you let z equals to a plus b. What? Okay, sorry you let z equals to a plus bi, and then you have to write this again, either to remind yourself or to show the examiner that you actually know what you're doing. Okay, so a and b are always real. Then you expand it like we did just now, and then you simplify and manipulate to give yourself either one of the unknowns as the subject of the equation. Okay, then you sub it in, and then you slowly get this. Alright, okay, so right, you won't always get nice equations where you can use the cross method to solve for. Okay, so as you can see down here, you get this. You have to use the actual quadratic formula to solve for b squared. Okay, then you get plus minus, and then like what I said just now, b squared must always be positive. Okay, don't forget that. B squared more than 0. So you have to reject the negative. For this equation, it's easy for you to figure out which one is the negative one because it's minus 9 minus this, and both of them are real numbers. So b squared minus where -9 minus square root of 145 is definitely negative lah. So your final answer for b squared will be -9 plus root 145 over 2. Then this is where the tedious part comes in lah, okay? The one that I see already, I also get headache on. So you square root your b square to get b, and then make sure you got your plus minus sign, very important. Okay, then you basically, because they want it in exact solutions, right? So you can't really, you can't make a nice value out of this. Okay, so to say. All right, so it's tedious, I would say. These kind of questions are tedious. You have to focus a lot to do these kind of questions. In fact, any math question, you also need to have a level of focus that's up there, because you never know what they're gonna throw at you lah. Okay. So you sub in the negative value of b or the positive value of b back into this. Okay, and then from there you manipulate it, make it. What I like to do, right, whenever I'm facing this kind of weird chunky ass numbers, right, I like to make them look as neat as possible lah. Okay, so yeah, so basically you got this over 2, you just shift your root 2 up to make your working look a bit neater. Okay, and take note of the negative sign. All right, there's a equals to -4 over b, so -4 over. So if you sub in the positive, your a will be a negative, and if you sub in a negative, your a will be positive. All right. Then after that, very easily, you just sub in your a and b into this. Okay, similar to how we solved the question just now, except now that it's much more tedious because you have all these big chunks of irrational numbers. Okay, next part. Okay, come to the part where I only did for one value of w because I was running out of time. Okay, so what we see here is this, right? Basically, you look at it, it's basically z equals to iw plus 3. So you just substitute that into this equation, and then the solution for iw plus 3 will be equals to z, and you manipulate to make w the subject of the equation, like what I did over here. And then you sub in your z into this equation, which will give you this monster. Okay, what do you do when you see this kind of monster is you take a deep breath, and then you slowly, carefully reduce it all the way down to this. Okay, honestly, I think when it comes to this kind of big ass chunky answers, right, you get the teachers will be quite lenient with how you present your answers. But as far as possible, try to make them look as neat as possible. All right, so yeah. Also, you see that the denominator is I, right? For those of you who weren't here yesterday, what we went through was to remove the I from the denominator, you multiply top and bottom by I. Okay, so this is what's happening. Okay, so when you multiply top and bottom by I, the bottom will give you a resultant -1. Okay, and then you multiply this into here. Wait, actually, did I get the sign wrong? I think I got the sign wrong.
Correct. Because your right side, right, I divided by I is 1. So your view is correct. It's all correct. Yeah, don't worry.
Okay.
If it's wrong, I will yell at you.
All right. Okay. Yeah. Okay. So basically, because you get -1, right? You take out the negative from here, from this the top, right? As you can see, they're both negative. You take out your negative, and then the top here is this part of the complex number is multiplying by I. So I times I will give you -1. This sign will change to negative, which we pull out also. And then divide by -1 at the bottom here to give us this monstrosity. Okay?
Sorry, guys.
Yeah. I just showed you guys like the method with as to how you do this. And then you can just replicate it with the other value of z that I showed you just now. Alright? I'm so sorry, guys. It's a bit slow, I understand, but yeah, I haven't been doing this for too long. Okay, then we'll move on to the next question. I'll try to go as fast as possible. Alright, okay, so next two actually, yeah. So you see, right, what you get here is okay, we start from the top, from the second one first. Okay, w squared minus 9 plus 8i. Okay, so what we actually have is, if you see, iz. Actually, is this a good card? I don't think you guys can see. So let me erase this. Choose a new card. Blue. Okay, what you actually get is bracket iz square equals to -9 plus 8i. Okay, so when I see these kind of questions, right, where you have to substitute z with something, what I like to try to do is to, as far as possible, find out how you get back to the original equation, which was this, okay? So now we get iz square, right? As I mentioned before, I square is -1, is our favorite number. Okay, so z square will give you 9 minus 8i. So from there, we can deduce that w equals to iz. So what we do is, we just multiply I with the solutions of z that we found just now. Okay? So when we do that, sorry, I no water. What happens is, you basically swap around the positions of the real and imaginary parts of the complex number. And then also there will be a change of sign, because when you multiply this I with this I, you get -1 times negative sign, which will give you positive. Okay? So very simple. Okay. Now the last one, this is the most tricky one that even I have to do some, what I like to call, quick reverse engineering to solve. So right, you see this, I actually took like around 10 minutes to try and solve this, because I haven't do complex numbers in like damn long. Okay, so I'm just gonna give you guys an example lah, okay? So let's say you got two complex numbers, 3 minus 3i and 5 minus 4i. Okay, so you're gonna expand this, and then you're gonna get 15 minus 12i minus 15i plus minus 12. Alright, then what you get is 3 minus 27i. Okay, so what I did was, I took this as a main equation. Okay, So my guess when I first saw this w square equals to 9 plus 8i was that this might be a conjugate of z, because you see plus and minus. So you can have multiple guesses for this kind of question, and then for me, the fastest way is to go through all your guesses quickly as fast as possible, and then try to find out which one actually gives you the solution correctly. All right. Later on, we'll have another question that is similar under the polynomials part. Okay. So now we actually got these two. What I'm gonna do here is to multiply the conjugates of both these complex numbers, and then see what I get. Okay. This is actually how I did it, by the way, guys. So 27i plus 3. Okay. All right. Now you see something very magical has happened, right? Basically, when you multiply the conjugates together, you get the conjugate of this. Okay, let's say these are solutions of z, and this is basically z conjugate. Okay, what happens is that if you multiply z and then you get this, when you multiply z conjugate, you get the conjugate of expansion of when you multiply the roots of z. Does that make sense? Okay, I just gotta assume that it makes sense.
Basically, right, the idea is your w square will always give you two roots. The idea is that you take one of the root, you square, right? You square that particular root, you get back 9 minus ai, right? But now if we take the conjugate root and we square, we realize you get the conjugate of the original number, right? So let's say we have z squared minus 9 minus ai, correct? So z squared equals 9 minus ai. You have one root, let's say is some complex number w. Okay, the noise of it. Let's say it's v, right? If you take that particular root, you square, you get back 9 minus ai. But now, if you instead take v conjugate and you square, you get 9 plus ai, 8i instead. This is the conjugate of the equation, the original equation, right? So that is why your roots are all your conjugate. Whenever you see z squared equals to a plus bi, then after that they ask you find w squared equals to the conjugate, your roots will be the conjugate of the original roots as well. All right, I will send you guys the proof additionally in the addendum slide, because that one you don't need to know the proof, right? But the main idea is if you see w squared equals to conjugate, your roots are conjugate as well, right? Don't need to showcase anything. Just you can immediately write down the roots already. All right, just say that w equals to the conjugate root. You need to show that w is the z conjugate. Can?
Okay, move on to the next question, yeah? Chop chop, boys. Okay, next.
So basically, for
You
this
was explaining
slide,
the previous slides.
yeah.
Okay.
So if you have noticed thus far, right, all your roots are basically plus minus of each other. Okay. Yeah.
Okay. Next. All right. Now I'll give you guys 2 minutes. Okay. Let's move on. We got this quadratic equation with an imaginary number inside. What we're gonna do is, as you guys already know, use your quadratic equation. All right. Except the only tricky part that we have here now is that within the b squared square root b squared minus 4ac, when you reduce it down, you actually get a imaginary number inside. Okay, a lot of you might have, I don't know whether you got stunned by this or not lah. Okay, basically yesterday we showed 2 examples about solving quadratic equations with imaginary numbers in them, but I think the examples basically cancel out all the imaginary numbers within the discriminant. Okay, so basically what you want to do is for me, what I did was solve for it very quickly. You can also actually press your GC, because the answer is actually plus minus 2 lah. Oh wait, sorry, the answer is not plus minus 2. What am I talking about? Sorry.
It is.
Or is it?
Okay, when you key in your GC, root minus 8i. Okay, so what Zach did was he factorized out I, right? You actually don't need to. You can just type your GC root minus 8i. The GC is only going to give you one answer, 2 minus 2i. But if you see from the previous, well, 2 slides ago, any solutions to a square root, right, will be of the form plus minus bracket a plus bi. So you can just take that 2 minus 2i and put it in there. All right, so like what Zach did at the very last before he simplified for z. So at the very last step, you see minus 4 plus minus 2i minus 2 is the same as plus minus 2 minus 2i. All right, so don't worry about it. You can use your GC. Of course, if you see a terrible number, then you might need to go and solve again. Right, but in this case, we gave you 2 minutes because the question is literally just 2 or 3 marks. It means it's quite obvious that you can use your GC. Okay, so that is the clue. All right. So when you put 2 plus minus 2 minus 2i, then you can solve for the different roots already. Yeah.
Okay. Thank you, asmollizard. Okay, yeah. So basically, if you refer to my working, right, this is how you do it manually lah. If let's say your GC is broken like mine, so what you do is what we did just now, square root, how to solve a square root of the complex number. What you realize, you actually get b equals to plus minus 2. So even if you sub back in, you get plus minus 2. So the negative b will correspond to negative a, that kind of stuff. Basically what Lizard said just now, okay? So what you do is you find what your square root of negative 8i is, and then you sub it back in. Basically, if you have your GC, you get straight here. For those of you who don't have GCs and like to break things down and make your life difficult like myself, you do this, and then you get this thing here. Then you finally reduce it down to this. Okay, once you get to this, I think it's pretty self-explanatory. All right, you basically solve for 2 values of z, which are these. Okay. Okay, I think that should be quite easy. Okay, we'll move on to the next question. Chop chop. Okay, now we'll come to one of the most important skills for complex numbers, and personally one of my favorite things to say, comparing coefficients. Because this is basically a lot of eye power, and also actually quite a bit of writing also, depending on the question that you get. Okay, so comparing coefficients, right, what it means is that, like, I think we actually did it, and we actually used this skill in the previous questions, where you compare the real portion to the real portion on both sides of the equal sign, and then the imaginary portion to the imaginary portion on both sides of the equal sign also. Okay, some of you might find this method very familiar, because it's actually a method that you use to solve polynomials as well. Okay, so now we'll start with this. What you have here is 2 equations. All right. Very simply, you're gonna do a simultaneous equation. Okay. The question is nice to you in the sense that they have already they made this part of the equation very straightforward. Okay. So all you gotta do now is, to make your life easier, you always avoid substituting into the square root, because why would you make your life hard? So what you do is you substitute, you manipulate this equation, and then you make w the subject, and then you sub whatever w is back into equation 2 over here. Okay, so what you get is this equation, which you then expand, and then you simplify to get this. Now once you get here, you use your quadratic equation again to solve for z, which will give you this or this. Okay. Then what you do next is, like all simultaneous equations, you sub back into the equation of W, which is equation 1. Which will give you these two answers. Okay. So everybody's happy. You got your answers. And then move on to
Your
the
your
next.
your arrow, the right solution goes to minus I. So right,
Oh,
for this
sorry.
case, right, we must be very careful, right? So it's not that you can leave it as z equals to 2i equals to minus I. You have to put z equals to 2i, comma, w equals to minus I minus 2. Or z equals to minus I, w equals to minus 2 minus 4i. All right. So just an aside also, just to warn you guys also. So you guys saw that z obtained a quadratic equation, z squared minus I z plus 2 equals to 0. An alternative method, which I really recommend this method instead, is you let z equals to a plus bi. Then you expand and then you solve the real and real, imaginary, right? Because sometimes the quadratic equation, the square root might be another complex number. Then you get a whole lot more problems again, all right? And the worst, and why I don't recommend the quadratic method all the time, this time is okay because you actually, if you can see it, b squared minus 4ac gives you minus 4. Because sometimes, which happened for my prelim paper, they give you alpha as one of the coefficient. You cannot do anything to the b squared minus 4ac with alpha inside. Yeah. Okay, so I do recommend that you do the z equals to a plus bi method when you have an equation just with z or just with w. Okay. Yeah. So this is just a comment. Yeah.
Oh yes, yeah, because this is supposed to be under comparing coefficients.
But we'll upload the solutions. I'll upload that solution as well. So don't worry about it, guys. We'll
Right.
in the point of this lecture is to show you different types of solution. Yeah. Okay.
Okay, yeah. So we'll give you both ways to solve this equation. Okay, so you have one normal way which most people will just directly dive into, and then you have a more efficient way which Lizard will show you, will provide. All right.
It's kind of like more like the other way around. Because your one is more efficient than doing the a plus bi. But no, let's just
In
move
this
on.
case, in this case, mine is more efficient, but under certain circumstances, the a plus bi method might be faster and safer also, like he just explained just now. All right. Okay. We'll give you 5 minutes to. So now you got two equations again. But this time you realize that we tried to play punk with you by giving you a conjugate instead of a nice complex number. Okay, so what you're gonna do here is to rewrite it again, manipulate it such that you get one, like for one equation you get a subject. So for myself, I manipulated the first equation such that W is the subject, and then I sub this equation into equation 2, which will give you this monstrosity. Okay, when you see such long and frankly intimidating expansions, don't need to worry so much. Take a deep breath first and then attempt it. Okay, so like what we did just now, as Lizard mentioned, sometimes you want to substitute your z to let it become a plus b. In this case, we need to do that because there isn't any way to change z to z conjugate into a similar form of z other than through assuming a plus bi. Okay. Next, we're gonna continue to expand and simplify, chop here, chop there. Okay, until we get this very, very long equation. Okay, at this point in time, you might think, what the heck is this? Okay, don't worry. Okay, stick to what you know, right? And so recall that this part of our lecture today is considered under comparing coefficients. All right. So what you're gonna do is you're gonna compare the imaginary parts with the imaginary parts and the real parts with the real parts on both sides of the equal sign. Okay. Okay. So over here, we got the comparison of the real parts. Here, we've got the comparison of the imaginary parts. Okay. Now what you see over here is that when you try to simplify both sides, you realize that for the imaginary part, for the parts with b actually cancel out. Alright, so directly from the imaginary part, you'll be able to find what a is, okay, which is 11 over 2. Okay, so now we've got a. What you do, right, is you substitute a back into this equation. Alright, and then you start to solve for b. So basically now, because a and b are part of z, you have found z, which is 11 over 2 minus 15 over 2i. Alright, so what we do next is we substitute z back into this equation. But take note that we've written this equation in terms of z conjugate. So remember that your z conjugate is a minus bi. So what, as you see, I've done here is to change the sign, okay, from minus to plus. So after you do that, you simplify and then you get this answer. This is what your W is. All right. Okay. So when you see this kind of questions, right, which will somehow lead you to making very long expansions, and you have to read like a long line of numbers, and your eyes are strained because you need to look at all these variables and i's and b's and a's. No need to worry. Okay. Take it slow. The whole point here is to make sure at this juncture you don't make any careless mistakes, okay? Because whenever you see such big and long chains of numbers, right, there's a very high tendency for you guys to make careless mistakes, okay? So don't be afraid of these reduction of your values. Take it slow, and just make sure that you are writing things out carefully and there's a flow of thought when you're attempting these questions, okay? Yeah, that's all I can advise you for such kind of questions, okay?
Okay, another thing is, for this question is quite nice. You can get the value of a from the imaginary part, right? But sometimes you cannot, right? Sometimes you can't get a immediately, sometimes you can't get b immediately. So instead you'll get an equation with a and b on one side, another equation with a and b on the other. Then you guys can probably know what to do lah, right? You got two equations in a and b, simultaneous equations, another simultaneous equation, solve a and b, then you get the complex number of Z. All right.
All right. Thank you, Lizard. Okay. We shall move over to the next question. All right. Now we'll be going through polynomials. Okay. Honestly, my personal favorite. Okay. Few things to know about polynomials, as we have said yesterday. When you have a polynomial with all coefficients that are real, and you have a root, and you have a solution that's a complex number, the conjugate will also be a solution to the polynomial. Okay, so keep that in mind. Okay, whenever you see polynomials with coefficients that are all real, always keep that in mind, because that's a very important and that's something very important for you to remember, because it will really make your life easier in terms of how efficiently you finish that question, and how hard the question will seem to you. So yeah, okay, now let's start. Okay, we're gonna start with this question. Are we gonna give them time to do this also?
No, the first question always be solve first. We show them the way first.
Right, okay. So as you can see down here, the hint, we gave you two hints. Okay, one is to expand using your GC, and comparing coefficients.
This time around, you just need to compare one. because it's only one variable, a only. Unless both bian, right, suddenly, I don't know real parts on both sides, then okay. But usually, you just pick one, pick the easier one to do. Yeah.
Okay, let's move on. Okay, so very quickly, I think we're running out of time. Okay. What you wanna do is you're gonna sub in your 1 plus 2i into this. Okay, shit. Sorry. You're gonna sub in your 1 plus 2i into this equation over here. Then you just slowly reduce it all the way down to this. Okay, like we said just now, when you sub in your 1 plus 2i, this will give you 1 plus 2i to the power of 4. What you're gonna do is you're gonna jam it into your GC and then get this. Then you see z cube also, you're gonna do the same thing. Okay, you're lucky that this one didn't give you z square, otherwise you have to do that 3 times. Yeah.
Yep.
Okay, so after
It's
that
not
you
that
reduce
difficult,
it all
you
the
just
way
need to go
down.
to a calculator
What?
history, then just change the power.
Yeah, man.
Yeah, just go to a calculator history, change the power. It's not that difficult. Yeah.
Yeah, but you know, anything not to waste time moving your hand from the paper to the GC, okay? Alright, so we reduce it all the way down to this. And then from here, like what Lizard has already said, you're gonna do comparing coefficients and compare the imaginary to the imaginary and the real to the real, okay, which will both give you a equals to 2, okay, easy. Next. Okay, like I said just now at the start, okay, very important to take note that if you see a polynomial with all real coefficients, then z conjugate will always be a root of the polynomial, okay? So with that said, if the polynomial doesn't have all real coefficients, it's not guaranteed that if z is a root of the polynomial, that z conjugate will be a root of the polynomial also. So that's to say that it can happen, but not necessarily. Okay, that's only if the coefficients are not all real. Okay, important to take note. Some people actually get confused with this. Okay, next. Alright, so continuation from that question. Okay, if 1 plus 2i is a root of this, find the remaining roots. Okay, so what you see I've written over here, right, is basically what I said just now. Okay, in exams, if you write just this, they are not gonna penalize you, they'll actually give you the mark because you're showing that you actually understand the concept. Okay, next, what I did was, given that I've got 2 roots already, I will just expand them to get a quadratic form. Okay, then because these 2 are roots of the original equation, I'm just gonna make it, and then you see that the highest index is 4, you have a z square. So from here you can kind of deduce that you can expand it into 2 different quadratic equations. Okay, so what you have now is I've written it out, z squared plus bz minus 5. So what I'm trying to do here now is to find the value of b. Okay, basically now that I've gotten this equation and I'm trying to form 2 different quadratic equations to find out the remaining 2 roots of this equation here, right? I'm just gonna look at the front and the back. Okay, so this is to make your life easier. All right, when you have 2 quadratic equations, the constants will always multiply to give this. So 5 times negative 5 will give you negative 25. So from the quadratic I've gotten from 1 plus 2i and 1 minus 2i, the constant was 5. Okay, so the remaining quadratic equation that is part of z4 minus 2z cubed plus 10z minus 25 will be negative 5. And then we see in front that the coefficient of z to the power of 4 is 1. So what we can deduce here is that the coefficient of z squared will both be 1 also. Alright. So basically, we've already excluded the need to solve for the coefficient of this and this from the unknown quadratic equation. Alright. So this is a secondary school method. I believe all of you should know how to do this. Okay. You compare the coefficients of one of the variables or one of the terms inside the power of 4 equation. Okay. So for me, I chose Z. Okay, because you won't need to do that many multiplications just to find out what B is. Okay. So from here we get 5B, 5 times B, and then negative 5 times negative 2Z, which will give you 10. Okay, so you compare the coefficients, you will realize that B is 0. So in fact, this equation will just be Z squared minus 5 equals to 0, which will give you Z equals to plus minus square root of 5. Okay, so that's how you do it. All right. Next. Okay, then now we got this. Okay, it's if you guys haven't already noticed, it's similar to the part earlier on where we have to substitute Z equals to something. Okay. Now, when you see these kind of questions, most of the time you can just I power it. Okay. I think this one should be quite easy to I power. Okay. Basically, you replace your Z with 1 minus W. Okay. And then you rearrange the equation such that your 25 is now negative and on the left hand side of the equation. Okay. So Z equals to 1 minus W. And then you rearrange it to make W the subject. And then you just suck all your values of Z back inside to get all your answers. Okay. I think there shouldn't be much problem with this, and I don't see any areas where you guys need to pay attention to. Yeah. Okay, we'll just move on now. Okay, we come to this one, which is more complex. Okay. We'll give you.
Actually, no, we just okay. You guys try on your own. The answer is there, but for this one is quite easy because they give you in REI theta. So you just apply the different properties of complex numbers, where especially with Z power n. So you just sub in the exponential first, and then you resolve, right? So for example, you look at Z cubed, right? You put in the exponential form, you get 27 EI 2 pi, right? So you know that EI 2 pi is 1, so you get 27, right? So you do that first, and then you put to Cartesian, and then you solve. Okay, so the workings in the next slide, and then I think we'll continue. Yeah.
Okay, yeah, I'll go through it real quick. All right. Looks like a lot, right? But it actually isn't that much. Okay. So firstly, what we do is we reformat. Okay, reformat. We'll reformat the exponential form that was in the question to put it in terms of your Cartesian form. I think some people might not prefer this way because now you have to deal with a square root. Okay, but for me, I like to look at it in terms of a Cartesian form rather than in exponential form. Okay, next you just sub it in, and for me I had to do it manually because my GC is broken, but you guys can just use GC and then substitute it all into your cube. Okay, then you slowly reduce it down to this, and then from here on you just use the comparing coefficients to solve for A. All right. Okay, then next, to solve for the remaining parts, what you're gonna do is actually press GC lah. You can press GC for this question, right? It didn't state that.
Yeah, but regarding the calculation, right, you shouldn't. Okay, I don't recommend you guys to press GC for the where you guys are spending the squares and the what, unless you guys are very familiar with square root 3 and square root 2. like the actual values of square root 3 and square root 2. Then you can go press GC. But then I tell you, you better don't because imagine you get like square root 3 over 8 is some weird number.
Yeah.
Right, compared to, square root 3 is 1.707, or is it something like that? Then square root 2 over 2 is 0.707. Yeah, so I highly don't recommend you press GC when there's like square roots and stuff. Oh, square root 3 is 1.732, okay. Yeah.
Alternatively, right, what you can do is, because you see that all like what I wrote here, right, all coefficients are real, so this is also a root. What you can do also, right, is to create a quadratic equation using these two, and then from there you basically divide it, and then you find what the remaining root of z is. Yeah. That's
for solving the polynomial, yes, you can. Yeah.
Okay. Last part of this question. Okay. 8z cubed plus 15z squared plus 5z plus 1. Okay. In case you guys haven't really seen the pattern, what you gotta do is basically you divide the entire equation by z cubed. And after you do that, it will be in the same form as the original equation over here. Alright. So I've written it down as z1, which is what the original z is, and 1 over z2. Okay. Yeah. So what you do is basically you just sub in all your z values, and then you will reduce it down all the way to these answers. Okay. I don't think I need to explain much for this. Yep. All right. We'll move on to the next one. Okay.
Same thing, just go through.
We'll just go through this in the interest of time, okay? So now you have this weird ass equation, and then they have given you A, B, and C as the roots. So you know there are 3 solutions. Yeah, you can kind of tell like it's a cube. So now they give you A equals to 1, and they ask you to find the real number of k. Okay, what you're gonna do here is very quickly you just sub in A equals to I into the equation. Then you get this. You reduce the equation down to this. And then from there, you will just do your comparing coefficients. So 4 plus 2k will be equals to 0. All right. There you get k equals -2. All right, but this question, right, probably I'll fault for not writing it nicely. What you're supposed to do is actually to use the value of k that you found here. I know some of you might think that we'll always like be damn pissed off at Cambridge for not writing like for not having a question continuity. So you don't know whether you're supposed to use the value of k that you've already found or something like that lah. Okay, for me, I got quite angry about that a few times. But okay, moving on. So now you've got z equals to what I as a solution. What I did was I used long division to find the quadratic equation that I got here. Okay, z squared minus iz plus 6. So from there, what I did was quadratic equation again to find out what the remaining 2 solutions of z is. Okay, now we go back to the question which said that arc B is less than arc C. So I'm gonna draw a quick Argand diagram over here, okay, to remind myself that B is in the bottom half of your Argand diagram and C is on the top half. Okay, as we see, the solutions that we actually got are both imaginary. Okay, so they'll lie on the vertical axis. Okay, but then because you see that arc B is less than arc C, obviously the answer that lies in the bottom half of the diagram will be B, and then the answer that lies in the top half of the diagram will be C. Alright, so that's what we get. Okay, B equals -2i, C equals to 3i. So using what Lizard has gone through in the first few slides, you're gonna reformat your answer and put it in the exponential form. Okay, take note that there's no more negative after you add after you put it into your exponential form. Okay.
Okay, just a quick correction. So what you should do, right, is you plot the 2 pointers, then compare the argument. because sometimes the roots might be on the same side. Yeah, so just be careful. Yeah. Let's go. Last few parts of complex numbers. And this part is actually quite simple. The logic is quite simple because you're dealing with argument. All right, so this part is called solving arguments. So why is that so? So the next few types of questions, you see a lot of z power n, z power a. Basically, you have a variable now n, and they equate it to a complex number. So now the question is, okay, maybe the question is find argument of z n, or find the least value of n. I think you guys probably have heard of it before, least positive n, or two positive numbers of n that gives you the argument. So what we do is every time we want to deal with argument, always go back to your exponential form, because Cartesian doesn't really tell you anything about the argument unless you do tangent inverse y over x. And Cartesian is quite difficult to manipulate, as you have seen earlier. It's I to consider all this and all that. But for exponential form, it's just angle, argument, and modulus. So we know that, well, mod zn is 2 root 2, so whatever that is. But now the question is the argument of zn equals to pi over 4? Because as you can see, it is, right? And I'm here to tell you that it is, but not completely. All right, why is that so? So if we recall from yesterday, we talked about, let's say your argument or your complex number is over here, right? This is your complex number, 2, 2, 2 plus 2i. If you were to rotate it completely one round, which is 2 pi, it will end up in the same. And your argument is pi over 4 plus 2 pi. Rotate it one more round, it's still the same point, but now you rotated one more round, so it's plus 4 pi. Conversely, if you rotate it the other way around, you get back the same, but now it's pi over 4 minus 2 pi. So what does this mean? So instead of your complex number have the argument of pi over 4, in reality, your complex number, the argument is pi over 4 plus 2k pi. All right, in reality, all right? Or you can represent it as it is congruent to pi over 5. So it's similar to pi over 4 in the context of complex numbers. So it's the same idea, right? You just rotate how much you want to rotate about in the Argand diagram. So why is this important? Because as you see in the next example, this one, you notice that you can't get a perfect pi over 4. All right. So disclaimer, you need to add 2k pi or use a congruent sign when you're finding or solving for an unknown argument. In this case, z power n. So argument of z equals to minus pi over 12. Find the smallest positive value of n and corresponding mod z such that zn equals to 1 plus I root 3. So we compare argument first, right? Because you can't really compare modulus, right? It's so weird. Because now you have z power n, your modulus is r power n equals to 2, right? You don't really know what is r, you don't know what is n, so you cannot really solve for the argument first. Instead, you can't solve for the modulus first. Instead, you should solve for the argument first. So we know that 1 plus I root 3 is 2 ei pi over 3. So look at the argument. We have pi over 3 for 1 plus I root 3. On the left, we are told that, well, argument of z is minus pi over 12. When you raise the power of z, raise z to the power of n, the argument is n times minus pi over 12. Get minus n pi over 12. And problem is this, n is positive, which means this whole number is negative. And minus n pi over 12 is negative. It will never ever give you pi over 3. Right, so what can we do? So the idea is, this is pi over 3, and given pi over 3, this is a complex number. Your zn is going this way, this way, this way, going in the opposite direction of your argument. And this will be the argument of z power n instead, right? So it's now out of the principal range, right? As you see, we have this angle as the argument for z power n, all right? So what we have is, we now know that this is 5 pi over 3, right? Because one whole round is 2 pi, right? But now because it's moving in the clockwise direction, in the opposite direction, it is negative 5 pi over 3. We have minus n pi over 12 congruent to minus 5 pi over 3, or you can use an equal sign. Both are fine. All right. For me, I'll use a congruent sign because I'm just anal about it. All right. So equals to minus 5 pi over 3. Then you can solve for your n, right? In this case, solve for n equals to 20. Okay. Alternatively, if you are very sensitive to fractions, you know that n must be a multiple of 4 because this side would have a denominator of 3, right? You see, pi, then you have 6k plus 1. All right, you know that this has to be a denominator of 3. In order to get the denominator of 3, n must be a multiple of 4. And thereafter, you slowly work your way to minus 5 pi over 3. It's the same logic as before. You still get n equals to 20. All right, so whatever path you take, it will lead to n equals to 20. All right, so let's try this out together. Same idea, but first, you guys will try to express z in REI theta. Give you guys 2 minutes for expressing that, and then I'll guide you through the next part. All right, the first part is slightly familiar, hopefully. Okay, so we have, if you haven't noticed, z equals to EI 3 pi over 16 plus EI 7 pi over 16. Why? You notice you have this pair with that, this pair with that, to give us that. 2 exponentials in 1. Then remember, what do we do if we have 2 exponentials in 1? We pull out. One way to do it is the long way. I add this additional step to illustrate my point. First, you factorize out EI 3 pi over 16. Bracket 1 plus EI 4 pi over 16, or pi over 4. But then, well, we apply the half angle trick, right? Because is this familiar? This form is familiar, right? You have R plus REI theta. Then we factorize out, we get this. Then we use the identity EI theta plus EI minus theta to give us EI 5 pi over 16 to cosine pi over 8. So we have our R, we have our theta is 5 pi over 16. Our our modulus is 2 cosine pi over 8. All right. Alternatively, if you are familiar with this technique, we can straightaway jump to here, the average angle trick. Okay, now we have z power n as something root 2 EI 3 pi over 4. All right, how to get root 2? From here. All right, so minus 1 minus I would simply be root 2 will be your modulus, because 1 squared plus 1 squared is 2, then you square root it. Then the argument, well, be careful. This is in the third quadrant, so it is over here. Your basic angle is tangent inverse 1 pi over 4. So your argument is minus pi plus pi over 4. That's why minus 3 pi over 4. All right, then we times k because that is k. Then we also have the argument for z. We can sub that in. All right, from here, we compare the argument. 5 pi n over 16 equals to minus 3 pi over 4 plus 2k pi. Because again, n is a positive integer, which means that this will never be negative, but we want a negative angle. So 2 ways to do it. Either you figure out that, oh, okay, it's the same denominator, so I must get denominator 4. N was 16, so must be multiples of 4. You try n equals to 4, n equals to 8, and then see where you land. Alternatively, what you want to do is, from here, you know that this has to be positive. So what is the complementary angle to this is 5 pi over 4. Okay, not really complementary angle, but what's the there's not really a proper math term for it. I think there is, I just can't remember. So you know the opposite is 5 pi over 4, right? Then you get 15 pi n over 4, sorry, over 16, n equals to 4, right? Now, let's say they don't just want the smallest positive integer, they want the two smallest positive integers. Then what you do? Plus 2k pi. Then you solve for n. Oh, sorry, just plus k pi. Sorry, just plus pi. 2 pi. Because it's positive, so you add 2 pi. If this was negative, let's say if this was negative 5 pi n over 16 instead, then you must minus 2 pi. Because since n is positive, The more you add n, the more the angle will go in the opposite direction, aka the negative direction. That's why you must minus 2 pi now. All right. I mean, of course, 5 pi over 4, then you won't get the answer really. You need to like minus 2 pi minus something else. All right. So play by ear. All right. But idea is the same logic. You can either think it from the Argand diagram or through this, or if you want, there's a way actually, is involving algebra. All right, which I'll introduce in this part. Now, you might have come across questions where they ask you that is, find the argument where it is purely imaginary or purely real. So here's the thing. When you talk about purely real, all your points would be on the real axis, aka the horizontal axis, aka the x-axis, right? The problem is, it can be 1, it can be 3, it can be minus 25 and all that. So how do we know whether they are real or not? What do they share in common? Their argument. If it's on the real side, it is 0. If it's on the imaginary side, it is pi. Right? Same thing for purely imaginary. It can be minus I, minus 2i, it can be root 3i, it could be root 24i. But the idea is that their argument is the same, which is on the vertical axis, the y-axis, so pi over 2, or minus pi over 2. Similar logic as finding our argument. It could also be 2 pi, it can also be 3 pi, it can also be minus 2 pi, it can also be here minus pi. Similar for pi over 2, it can be 5 pi over 2, it can also be minus 3 pi over 2. Same thing for our bottom. You get 3 pi over 2 or minus 5 pi over 2. But you notice that from here to here is plus 2k pi. From here to here is minus 2k pi or minus pi. So in reality, it's the same logic, right? Now, the difference is what we look here, the 2 pi is if you're looking at purely positive or purely negative. All right, so this part's here. Otherwise, if you look at imaginary, so go back to this Argand diagram, you notice that it's pi over 2, right? If you want just purely imaginary, it can either be negative or positive. So you can go by here, plus pi, then plus pi another, and then go and so on. Same for our real. If you have positive real, if you add pi, you go to negative real, which again is still purely real. So that is why for purely imaginary and purely real, it is pi over 2 plus k pi, or for purely real, it is k pi. And it's not a concern for you now, but I'll show you a counter example later on. But using argument only works if you have the argument in n pi over k form. Otherwise, it's difficult, all right? And usually k is an integer, n is an integer as well. All right. Otherwise, you need to really whack with Cartesian, your algebra form. But if that's the case, then the question will be slightly easier and it will be another approach. All right. It'll be the comparing the coefficient approach. All right. So this is just for, this slide is for your reference. If you guys need a quick cheat sheet, so positive imaginary, negative imaginary, positive real, negative real. Positive imaginary is your vertical side, so it's pi over 2 plus 2k pi. Negative imaginary is at the bottom is minus pi over 2 plus 2k pi, because you can just keep rotating. Same thing applies to our real and negative real. All right, now I'm gonna go through this question first. So let W and V be complex numbers where mod W equals to mod V, the whole thing squared. Argument of W is pi over 4, argument of V is pi over 6. Find the modulus argument of V squared over W. So we keep everything in exponential form because we are dealing with division and we have to find the modulus and argument. So we have V equals to AEI pi over 6. All right, why A? Basically just give it any value, give it any modulus you want. All right, can be A, can be R, can be B, can be anything, right? Just don't put V there again, or nor W nor N. All right. So we let V equals to AEI pi over 6 because we have the argument for V, which is pi over 6. And then we have W equals to A squared, because if V mod V equals to A, then mod W will be A squared. So A squared EI pi over 4. Put them together, so I can return this out just now. You get EI pi N over 12. So our modulus is 1, our argument is pi N over 12. Okay? So we know that our argument is pi N over 12, right? And they are saying that we want this to be real. And then for these powers of, for these values of N, find the corresponding value of V squared over Wn. All right, so we know that v square w power n is ei pi n over 12, so it's not a big deal. Okay, so here's a catch. All right, here's the funny thing. All right, you won't believe it, but I already know the corresponding value of v square over w times n. It's likely plus minus 1. Because your modulus is 1, and it's probably going to be plus and the negative side. All right, but that is for experience. Let's just solve it the proper way first. Okay, so we want it to be real. So we want it to be on the horizontal axis with argument 2k pi, or odd numbers of pi. So it's actually just k pi. Right? So argument n pi over 12 equals to k pi. Ways to do it. Either you go through the denominator way and figure out that n equals to 12k, or you do it basically just times the other by 12 over pi. Right, so k pi times 12 over pi equals to n would give you the first one on the left, then the numerical one is the denominator one, you know that n is a multiple of 12. Right, either way, just keep on substituting k equals to integers, because k must be an integer, because otherwise you won't get real. So you get n equals to 12, 24, 36, so on and so forth. We're only interested in the two smallest positive integer, hence we get 12 and 24. All right, but basically we get k equals to 1 and 2. So we sub in back, we get for 12 we have ei pi, for 24 we have ei2 pi. This will give us 1, this will give us minus 1. All right, ei pi is on the negative real axis, 2 pi is just nice 1 row. Okay. Anyway, so we're able to solve the purely imaginary real questions because we have the argument in terms of pi. However, what can we do if we don't have argument in terms of pi? Let's say we have tangent inverse 4.8 over something, or we cannot get right theta at all. Well, we leave it in Cartesian, right? The only way out, because trigonometry form is kind of like Cartesian, so that will really help you. Idea is to compare coefficients, but now here's a difference, all right? If they tell you these are the two terms that you might use interchangeably, if you see purely imaginary, think of real part is 0. Because if it's purely imaginary, you have to have a real number, so you can compare and consider and compare the coefficients in the real portion. Same thing for purely real, is now the opposite. Your imaginary part is 0, so only consider and compare the imaginary portion, right? So this question, I will make you guys do it, but I'm just going to show you the variants or types of questions that you might get, right? This is one of them. Quite rare, okay? It's quite rare. But nonetheless, the working is right here. All right. So as I mentioned, if you want to try it's real, if you think, oh, it's real, purely real, try to find IRI theta, you're out of luck. Right. If you try like let's say REI theta and KEI phi, you won't get anywhere, trust me. Right, you won't get anywhere. Okay. So you can't really do the exponential trick here. All right. So don't bother. Instead, whack with Cartesian. All right. And the next few slides will prove traumatizing for some of you. Okay, now I'll go through one by one. Okay, so if this is real, this fraction is real, u plus v, u minus v is imaginary because we have I in front here. So I took out the I times something, a complex number, if it only gives you a real number, this must be purely imaginary as well, right? Because if let's say you have a plus bi, then you notice that you have ai minus b equals to ki. Sorry, you get a real number, right? You know that a must be 0. So it must be completely imaginary. All right, that's the logic behind. So we know that it's completely imaginary. We just need to consider the real part as 0. Then I whack this in, u equals to a plus bi, v equals to c plus di. All right, then I'll get this. All right, take your time when you substitute in u and v together, and then you get a minus c plus b minus di. Rationalize the denominator. Then, so here's the trick. You do not need to expand everything. We just need to consider the real part equals to 0. Right? Now, we know that this is rationalizing the denominator, so they are conjugates. Since they are conjugates multiplying each other, we know that the denominator will be a real number. Right? So we can leave that. Right? Don't have to consider much for this one. But for the numerator, we only want the real part, right? And we're gonna get this times this. So what I do is group them together. Like what we've done earlier in algebra, take the real, consider the real together and consider the imaginary together. So my real plus A plus C, in order to still be real, I only can multiply with the real part of the other factor, right? So A plus C times A minus C, because I only want to consider the real part equals to 0. Is there still any other real parts? Answer is yes. Our imaginary times our imaginary will give us a real part as well, right? So B plus DI times minus B minus DI. So I only consider the real part, this has to be 0. So you see, I didn't even consider the imaginary part at all. I didn't even waste time finding A plus C times B minus D, then B plus D times A minus C again. I'm not in the mood to waste that much time. Just consider the real part, all right? Do some rearranging. A squared plus B squared equals to minus C squared minus D squared. A squared plus B squared equals to C squared plus D squared, which are the square of the modulus of each complex number, mod U equals to mod V. How many marks was this question? 3 marks that you can gladly give away if you're good at the other questions. Okay, but you probably get some meta marks, like maybe down here you probably get 1 meta mark, 2 meta mark along the way. Okay, so that is purely real and purely imaginary, and we hit the last part of our complex number geometry and vectors. But it's not as traumatizing as vectors because it's really just basic vectors. All right, every time we talk about complex numbers, or actually in fact we look at graphs, let's say we talk about this point, right? We know that this is 3, 3. We can always look at it as vectors. All right, we see this point moving in the direction of 3x and 3y, or in the direction of x and y. All right, so same thing. Let's say if another complex number or another point, let's say this is the point here. Let's say we have this point A and this point B. We have this direction vector as OA, this vector as OB. Then, if we want to find, let's say, OA plus OB, we just go OA plus the direction of OB. So if OB goes on this way, it will be this way as well. Right, so this is OB as well. And then you get the final point here as OA plus OB, or simply A plus B. All right, so think of complex number as geometry whenever they ask you to sketch random points. And this is the biggest clue. When they tell you to, when you have these similar phrasings, on an Argand diagram, label and mark the points, then you already know it's a geometry question. Right, because they won't tell you to pull out Argand diagram. You notice that none of the questions have told you to sketch on Argand diagram the following points, and then, okay, that's it. Happy days. No, when they tell you to upload an Argand diagram, there's a reason behind why they tell you to upload an Argand diagram, and it's to find a particular shape. All right, so I'm going to go through this with you. We have z equals to root 3 minus I. On an Argand diagram, label and mark the points A, B, C, which are the points z, iz, and z plus iz, respectively. Then state the geometrical representation of OABC. So, told you, Argand diagram, they won't ask you to plot for fun. There's a reason behind it, because they want to ask you the shape of OABC. So we have the axis. Now, I know a lot of axes you see, I have this double-headed arrow. In the Argand diagram, it's the same as a Cartesian, just the normal axis. All right, but this time around, origin is still there, but imaginary and real. Don't put x and y. All right, if you put x and y, is I think it's 1 mark or half a mark. Can't remember. Depends on the mood of your teachers. All right. So we have point A, right? Because it's root 3 minus I. It's in the 4th quadrant, so we just write it down as point A. The dotted mark, please don't write a solid mark because it's not associated with a solid mark. You can write a dotted mark, dash lines across to mark out your point. But ultimately, you try to shade the ultimate point. Otherwise, in the exam, because you can use a pencil to sketch your graph, if you just have a dot there, it's kind of difficult to see. And don't forget, your papers are scanned copies. Okay, so don't put it too light. All right, so we have point A, and this is Z. Right, point B is IZ. So if you recall from IZ, it is a 90 degrees rotation counterclockwise. Why? Because I is EI pi over 2 times Z. So your argument will be added by pi over 2. So you go counterclockwise by pi over 2. This will be a 90 degrees. Okay. Now what you should do is label Z and IZ. So this one will be Z. This one will be IZ. All right. Now we have Z plus IZ giving you C. So think of it as vectors. All right, so you have Z going this way, plus IZ, you are now over here, plus IZ going upwards like this, So going upwards like this to give you our point C. And this would be Z plus IZ. Another thing, this would be a right angle as well. Because it's plus IZ, it's the same orientation as you added for IZ to Z. Okay? So that is the first part. Now, second part is this. You see there's 490 degrees, right? It's either a rectangle or a square. So how do we decide whether it's a rectangle or square? Look at the magnitude of each of the sides. Okay. Now, to prove square and rectangle or differentiate between them, just compare two adjacent sides. So just pick this side and this side, which will tell you whether or not it is a square or not. So in this case, if you look at Isaac, the modulus of Isaac is still Z, right? You notice Z EI pi over 2. So the modulus is the same, which means this length is equal to this length. The OABC gives us a square. All right, you don't write all in caps. I'm just brainwashed by the army to write everything in caps. Okay, so it is a square, not a rectangle. So take note. Now, next part is hence determine arc Z plus Isaac. So this is what we've gotten. Right, so now we look at Z plus Z or Z plus Isaac, which is this complex number here. So first thing to do is draw across. Right, so you want to find this angle here. Okay, is this difficult? No. So why? Very simple. To get this angle, you need this angle minus away this angle here. Okay, let me choose a different color. So we want to get this angle, green angle, or right, blue angle, because yeah, you want to get this angle, red angle, minus away the angle inside. So let's use purple. So this angle here. Okay. So we have the purple angle actually because it's basically the argument of A, which is, let me use back blue. So argument of A, we know it is root 3 minus I. So it is minus pi over 6, right? Tangent inverse 1 over root 3 is pi over 6. Then it's in the fourth quadrant, so it's the negative of your basic angle. So it is pi over 6, right? Negative pi over 6, but you can just leave it as pi over 6 because we're not looking at it geometrically. But what's the angle of the red one? So if you don't know, we have O, B, C, and A. All right, these lines are joined. We now have O to C, and this is a square. The angle here is pi over 4, half of 90 degrees. All right, so we have pi over 4 minus pi over 6. So give us the argument on top. So pi over 4 minus pi over 6 times 3 times 2. So we get pi over 12. And that will be the argument of Z plus IZ. You want a clue? Here's your clue. Your clue is just right here. That is likely the argument. Otherwise, if you see a random weird argument like 11 pi over 12, there's also another clue that could be your argument or pi over 12 is your argument. Now, deduce that pi over 2 minus root 3 is pi over 12. So, well, now you basically need to find the coordinates of C, right? Because you have the argument of Z plus IZ, you just need the coordinates of Z and then use the tangent inverse, all right? So, well, you have to actually, you know that Z is Z plus IZ, so you need to calculate what is IZ, right? Because we already have Z, so IZ is simply times I. So we have minus I times I give us 1, then root 3. So we have Z plus IZ being root 3 minus I plus 1 minus root 3I. Sorry, 1 plus root 3I to give us root 3 plus 1 plus root 3 minus 1I. Then we have our argument as tangent pi over 12 equals to y over x. All right, this came from tangent inverse y over x equals to pi over 12. Root 3 minus 1 over root 3 plus 1. Rationalize the denominator, you get root 3 minus 1 square over, then below is just simply 3 plus 1, so it gives us 4. All right. All right, yeah, okay, then I think I'm right. Wait, hold on. I'm not able to do this on the wait. I get 4 minus 2 root 3. Wait, it's a bug. Wait, something's not right. Why the last part? Something not right. Wait, root 3 plus 1. 1. Why am I? Should be correct. C's. Yeah, okay. Wait, hold on. I think I might just be glitching. Root 3 square plus 1 minus 2 root 3 over 4. Oh, I think I might have left out the over 2 or something like that. Wait. Whatever it is, you'll get, apparently you get 1 minus half root 3. Oh, I know what's my problem already. Well,
Isn't your bottom 3 minus 1?
Oh, right, yeah, 3 minus 1. Yes, how to be a dumb child. Yes, it's to be 2. Yeah. I do too much complex numbers. You just start to forget your basic stuff.
It's
Sorry,
late.
guys.
It's late, guys. It's late, guys.
Oh, okay, yeah. It's like, hey, how is it? Yeah, okay, my bad. Yeah, okay. Well, note to self. Dealing with real numbers is a foreign topic now. Okay, I won't make you guys try this, but it's the same idea. You get a Argand diagram. Just find the modulus and argument of point of P. All right. Whenever you do it Argand diagram, try not to do it. You want to get the exponential form as much as possible. Otherwise, it is quite difficult, especially for P, where you have a over 1 plus root 3. When you need to convert it to a exponential form to make it easier for you, because you can't immediately sketch a over 1 plus root 3 immediately. All right. Same thing, you would then get just plot P and Q, and then you would then do the similar thing for purely imaginary. In that case, would be pi over 2 plus k pi. All right, so this is a question for you guys to attempt. I will draw out the remaining graphs for you. Otherwise, then yes, this is actually the last part of, wow, I actually have the answers there. Okay. Otherwise, then this will be the end of the lecture. What a way to end, man. End with a careless mistake.